Hello and welcome back to Tripplikit, home of interesting electronics. And today we're going to move on with the digital synthesizer tutorial. And we're going to take a look at how digital audio works and sampling. A lot of the examples I've created for these tutorials involve quite subtle audio effects which will be lost in YouTube's audio processing. So if you look in the description for the video, there'll be links to download the WAV files for the audio so you can listen to them properly yourselves. Also, the bits of code I use to create the examples will be available and you can download those. If you're interested in creating digital synthesizers, you probably already know the basics of digital audio. However, bear with me as I will be touching on aspects of digital audio that affect synthesizer design. Okay, here we have an analog waveform, a voltage that varies with time, and we want to make a digital representation of it. However, to be sure of capturing all the information in our waveform, we'd need to take readings at infinitesimally small time intervals with infinite resolution. Obviously we can't do this, so we have to take readings at regular time intervals and with a fixed number of values available. Note that this means that the readings are not completely accurate. So, for instance, in the case of a CD, we have 44,100 readings per second, each of which can have 65,536 possible values. These inaccuracies, both time and amplitude, have implications, so let's talk about each one of them in turn, starting with time. Everybody's heard the term sample rate, which is the number of readings per second. This imposes an absolute upper limit on the frequencies that can be represented at the sample rate we're using. So here, this detail is lost. This upper limit is known as the Nyquist frequency and is half the sample rate. If we try and represent frequencies above this, they actually appear as frequencies below it. The simplest way to think of this is that they are reflected down from the Nyquist frequency. For instance, let us consider this waveform. It's a sort of a ramp wave. I've generated this sound to keep the waveform shape constant but increase the frequency over time. So we play this. Incidentally, the program you're looking at is called Cool Edit and it's years old. The 2000 in the title's a bit of a giveaway. But it has one feature that I find really useful. It will display a spectral of the waveform over time. As you can see that the waveform you've just heard is made up of 5 frequencies and you can see them increasing over time. I then wrote a simple piece of software to create a new sound file from this one, but only taking every third sample. This new sound file is 1.5 octaves higher and only 1/3 the length. As you can see, it still starts out as a sawtooth wave. However, if we look at the spectral view of this waveform, we can see that when the harmonics of our sound reach the Nyquist frequency, they are reflected down, and if the reflection reaches the bottom, they are even reflected back up again. These reflections are not harmonically related to the original, so they sound very nasty. That's all a bit high, so then let's transpose this back down again to its original frequency so we can do a direct comparison. I've already done that on this sound file. So here it is transposed down again. And comparing that to the original. You can clearly hear the unpleasant background frequencies that have been introduced. So, while processing or generating digital audio, we must be careful not to have any frequencies in our sound that go over the Nyquist frequency. The resulting noise will make our synthesizer sound digital. However, like anything, this can be used to good effect. In fact, this is what gives FM synthesizers their bright, glassy, digital sound. Finally, textbooks will show you that you can sample any frequency up to the Nyquist frequency. And they'll show you this sort of diagram, the green dots being the samples. However, we could sample the same waveform like this, in which case we get no output at all. This interaction between the sample rate and the signal is still significant, down to maybe a fifth of the sampling rate, in our case about 10 kHz. In practice this is not a problem because all the frequencies we get above this frequency are things like sibilants and cymbals, which are essentially noise signals which mask any such interaction. Okay, let's move on to sample resolution. As I said earlier on, turning an analog voltage into digital numbers will give slight errors which result in what's called quantization noise. Domestic and semi-pro digital sound equipment in general stores samples in 16-bit resolution, which, if you use all 16 bits, gives approximately 96 dB signal to quantization noise ratio, about 6 dB per bit. This is plenty for sound reproduction. However, let us say we're developing a 16-voice synthesizer. Theoretically, each individual voice will have to be a 16th of the maximum amplitude, in case they're all going flat out at once, which is 12-bit resolution for each voice, or 72 dB signal to quantization noise ratio. In addition, every time we do a calculation we can introduce quantization noise. This depends on the calculation, but by the time we've generated our final output sample we can have done an awful lot of calculations, so this can add up to a significant amount. So what effect does quantization noise have? Okay, so here we have a sound, a sort of a sawtooth type wave of ascending pitch. There we go. So what I've done is made 16 versions of this with progressively fewer bits used. So for instance, the third version is 14-bit resolution. To get this, I simply cleared the least significant 2 bits of the sample. Here for instance is the 2-bit resolution version. As you can see, we only get 4 levels here. Now let's look at the whole file in spectral view, again using CoolEdit 2000. So shall we listen to this file? You'll need to download it to hear it properly. And you can see the quantization noise. It shows up as the sort of coloured snow. get a better idea of when the noise starts coming in, we can listen to the noise without the signal. This sound file is the same as the last one, but I've simply subtracted the 16-bit signal so that only the noise is left. Again, you'll need to download it to hear it properly. We'll play it anyway. Okay, the point I'm making is that it's important to be careful about losing bit depth, bit resolution, but it's not the end of the world to lose a couple of bits of bit depth, and plenty of perfectly good synthesizers and sound gear have been made using 16-bit systems, and I ought to know I made a few of them. Every electrical audio signal has an upper limit set by the supply voltage of the circuits that's carrying it. When the signal reaches this limit, it will clip, and this clipping will result in distortion, which will be harmonics of the signal. If we were designing an amplifier, we wouldn't want this to happen at all. However, in musical applications we can use this to good effect. For instance, if our circuit was using valves, only a few lower harmonics would be generated, and this can sound very nice, as any electric guitarist will tell you. In transistor circuits, this clipping is a lot more abrupt, a lot harsher, resulting in a harsher, fuzzier sound. In the digital domain, however, clipping does not naturally occur, and the numbers wrap round from top to bottom or from bottom to top. This sounds terrible, as I'll show in a minute, so to prevent this we have to make sure, if our calculation results in a number that exceeds the maximum value for a sample, we actually take steps to clip it ourselves. Okay, let's consider two signals. This one and this one. If we add these together digitally at 16 bits, we get this. Okay, to here, and then yuck. And why is that sounding like that? Because the addition has gone beyond the maximum values for a 16-bit sample and wrapped round, so this bit should be up here and this bit should be down here. However, if we clip the output, we get this. Which sounds a lot better, and we can see, if we look at the waveform, we can see here where the sample would exceed the maximum possible value, it's clipped here and here. However, this harsh clipping still introduces a lot of noise. If we look at the spectral view, we can see once it starts clipping we get a lot of noise right across the spectrum, and a rather cool pattern as well, but that's completely incidental. Okay, so for now we're going to try our best to make sure we don't clip any sounds, but in a future tutorial we will look at using clipping creatively to create fuzzy, distorted sounds. Okay, so far I've looked at issues surrounding bit depth, stroke resolution, headroom and clipping from the point of view of 16-bit samples. Fortunately, these days the increase in processing power has meant that 32-bit processors are now cheap and powerful. In fact, the STM32 we're using in the mean green is 32 bits, so I'm proposing to generate the oscillators at 16-bit, giving us plenty of headroom, and leaving 16 bits for the rest of the processing, which should be absolutely fine. Better still is to use floating point numbers, because in practice they have no upper limit, so you can't ever lose any resolution. This is not practical on microcontrollers because floating point calculations are very slow compared to ordinary integer calculations. However, on computers the processors now have hardware floating point engines, so the floating point calculations are as quick as the integer calculations. So you'll find if we ever do any VST plugin work or anything, that is always done in floating point. And finally, a note on linearity. Audio engineers are always striving the hardest to make their circuits linear. The total harmonic distortion figures quoted for amplifiers are a measure of linearity. However, in the digital world, our linearity is always perfect. 1 + 1 is always equals to 2, which can be a blessing. However, non-linearity can add warmth to a sound, specifically in filters, in synthesizers. So in a later tutorial we'll be looking how to introduce non-linearity into our perfectly linear systems. Well, that's about it for our look at the principles of digital audio. Next time we'll be taking a look at sampling. And yes, I know we're building a synthesizer with oscillators, however, bear with me, all will become clear. So, if you've found this interesting, please subscribe to the channel. If you've got any comments, please leave them. Don't hesitate to ask a question if there's anything you'd like to ask me. And that's it for now. I'll see you next time. So it's goodbye from Tripplikit, home of interesting electronics.